Hello and welcome to this session on urban studies at BSO 2022. We have 5 interesting looking talks here today. Hopefully you've all seen the programme, but first up we have a talk by Michael Kleiber and Matthias Haus on optimization of energy community in Switzerland, followed up by Derek Mitchell talking about simulating the built environment for another globally distributed species, which promises to be a nice, interesting talk as well. We follow up with towards universal building energy modelling, case of low income self-constructed houses in informal settlements in Lima, by a variety of people, but speaking is Argyris Orianopoulos. Then we have tailoring and demand reduction strategies for communities in India from the CEDRI project with David Jenkins. And finally, we have developing an open access plugin for urban building energy modeling in QGIS, with the speaker being Shyam Amrith. Hopefully you'll all enjoy these talks as much as I will. And so next up we have Derek Mitchell talking about simulating the built environment for another globally distributed species. Over to you, Derek. I think you're on mute.
I'm unmuted now. Okay. Can everybody see the presentation?
Yes.
Good. Right. I'm Derek Mitchell. I'm a postgraduate researcher at the Institute of Thermofluids at the School of Mechanical Engineering, University of Leeds. And this talk is about simulating the built environment of another species. And this is the honeybee. And so we'll be giving engineering introduction to the honeybee, the modeling of it, and then validating the model, a sensitivity analysis, and then the big thing, what does it all mean? Right. First, an introduction to the honeybee. Apis mellifera. Normally, we see them going in trees and in their hives. They evolved in Africa or Asia, we're not too sure, 6 million years ago. There are now 21 subspecies that have diversified over the last 1.5 million years. Their range is all the way from the hottest parts of the Arabian Peninsula to the wet and windy parts of northern Britain. And they experience temperatures from -40 to +40, and they utilize tree cavities in their natural state to actually weather these extremes. But from an engineering perspective, it's probably better to consider it more as melliferan daughters sugar refiners, because the hive is in effect, the biggest energy aspect of it is its use as a sugar refinery. This is where they take half a ton, typically a year, of 20% sugar solution and make it into around about 60 kilograms of an 80% sugar solution that we know as honey, which obviously involves a considerable amount of energy. But in another part of the actual nest, there's also the equivalent of running a maternity hospital, where they raise their young under very, very closely controlled conditions. That's using zone temperature control to get to sub-degree variation in the brood temperature at around 34 degrees centigrade. Humidity control, we're talking about 90% relative humidity at 34°C, where the brood is, compared to 50% relative humidity where the honey is being refined. And they're doing this using forced ventilation, the natural convection, and manipulating the various fluids. Now, when we model the honeybee in its nest, we need to actually consider the honeybees themselves. We do this by modeling them as a porosity and deriving this from spheres and effective spheres, actually modeling the bees as cylinders. Now, in order to do that, we obviously need the length of the honeybee, its diameter, and its porosity or number density. So we need to research a range because we're dealing with 21 different subspecies. So we're looking in the hot parts of the hot climate bees are around about 2.5 millimeters in diameter, and about 6 millimeters and vary up to 6 millimeters in diameter in Britain. The length varies somewhat as well, 10 to 14 millimeters, and the number density doesn't vary that much, from about 1.25 in the hot climates to 1.4 times 10 to the 6 per cubic meter in the cold parts of Britain. So when we actually look at the diffusion coefficient, we can actually see that there is quite a dramatic difference. When we look at the honeybees in the hot region, we can see the diffusion coefficient is around about 2, whereas the bees in the cold region are actually at around 50. This is more like a cubic relationship compared to the diameter of the honeybee, which means it's really, really significant in their existence inside the nest. And so what we've done in the modeling was actually to produce a CAD model of the hive. We didn't use radiation and no bee conduction, and we were able to simulate a large range of the temperatures they experience. Yes, we use 2.5 millimeter, 6 millimeter diameter bees, our cylinders, and we went through the full range of possible porosities, from the theoretical maximum density to there being no bees there at all. And we consider the bees as being evenly distributed throughout the nest. To validate this model, we actually we used the brood as an isothermal heat source. They keep their brood very close to their areas of brood, very closely at 34 degrees centigrade. And so we emulated that by some slabs of aluminium electrically heated, and then use surface temperature measurements over a hive that was being heated internally. And by using symmetry and an optimized Latin hypercube sampling method, we were able to, in fact, have an effective, very high number of sampling points over the surface of the hive. Now, in terms of validate, we're really having to cope with the reality of radiation. So, to do that, we use a lump model of the CFD and the experiment. And then we're able to substitute the CFD convection conduction results with the experimental validation to see whether they corresponded to the experimental heat loss. And in fact, we were able to get to quite a close agreement to within a few percent. The sensitivity, we went through the usual techniques of varying the sizes of the mesh, and where we're talking here somewhere between 3 and 12 million cells, 3 million cells proving adequate. We looked at issues with comb conductivity, the ambient temperature, and the ambient velocity. It turned out that current designs of hives are very sensitive to the ambient velocity, so we picked one where it wasn't going to be factored too closely. And in fact, that was about 50 millimeters per second. So what we found, the results, we found that size matters. We had this even distribution in the hive, and what we found is for small diameter bees, as you can see in this cross section between the combs in the hive, we get very, very high convection currents. But when we go to large diameter bees, such as you would find in a northern climate, these convection currents are dramatically reduced. To look at that in a bit closer detail, what we've got here is a plot of thermal resistance versus number density. The red vertical line is near enough the number densities we would care in both hot and cold climates. But as you can see, the cold climate bees actually have a much higher thermal resistance than the hot climate bees. Now, we can associate that quite readily, that cold climate bees want to be insulated, and the hot climate bees may want to dissipate heat at parts of the year. And this gives us a 2 times difference. And for the bees, this is a real big survival significance, or an evolutionary drive into trying to to do this. So the things we need to take away from this is we need to abandon quite a few anthropocentric assumptions about dealing with other species. We are used to ourselves in the various differences between ourselves not making any difference. Whereas in other animals, small subspecies differences can have a dramatic effect on how they deal and interact with their built environment. There are a lot of assumptions, even then, mammalian assumptions. For instance, assuming that heat dissipation is all around about the volume to area ratio of the individuals. And that gives a linear relationship. And here we're seeing a cubic relationship. And it shows also that the other species can have a greater interaction with their built environment than humans because of the differences of scale. The difference, if you think about the interpersonal distance between humans being of the order of, we could have it in the order of a meter, the interpersonal distance of a honeybee is about 5 millimeters. And given the viscosity of air, that makes a big difference. And these climatic differences and the way they interact have actually changed the way this animal, Apis mellifera, has actually evolved, making these small differences in diameter interacting, so the built environment has interacted within evolution. Thank you. We got any questions? Q&A.
I think we've had one come in now from Sukumar. What would a difference on the order of 1 to 1.5 meters between human scale and 5 millimeters, or 5 millimeters between bees?
Well, as you can imagine, it's the size of the orifice. If you go through the equations, it comes out making a much bigger pressure difference between resistance to airflow, which ends up with resistance to convection. So that we're used to the whole idea that humans don't actually really oppose the airflow inside a building. And so we assume that when we huddle together, we in fact improve the situation as regards resistance to airflow. In fact, we increase it. But it doesn't really until you get extremely close. Honeybees are already starting out with that 5 millimeter gap in their normal situation. So they start off from a situation of having high resistance, whereas we start off from a low resistance. Would we expect UK bees to get smaller as a result of climate change? Well, we would expect a migration of bees, different subspecies, to be able to do better further north. Our own subspecies, Apis mellifera, would end up needing to find somewhere a bit cooler in order to deal with it. However, honeybees are very adaptable, and they have different techniques. For instance, you might imagine what on earth does Apis mellifera do in our recent heat wave? Well, what they do is they either, in their natural environment, that isn't really that much of a problem because they're inside trees, and inside living trees, they've got effectively a cooling jacket, which is the water going up to be transpired. As regards when there is individuals, it all depends whether they know some of the tricks of their more highly, their other adapted cousins in the tropics, if they still remember or are still implementing things like in-flight cooling, which Apis mellifera scalata in Africa does. It actually puts beads of droplets of water onto its proboscis and evaporates them in flight. So
within your model, have you considered the humidity and the latent transport at all?
Say again?
How have you done moisture transport within the hive?
In this one, in this model, I haven't, because what we were running on that has large effects, and so the actual knowledge of what bees do inside the hive is, from a thermofluids point of view, is only at the beginning.
So have bees optimized hive design for their convective cooling purposes, or is there still a way for them to go?
Bees are obviously co-evolved with trees and the hollows inside trees. I must admit, as an engineer, every time I try and see, there might be a different optimal solution, I find that the honeybees have already got there. They've been doing this trick for 1.5 million years. And so by evolving, they've actually come up with quite some interesting solutions. For instance, the migration up into the upper part of the nest inside a tree. Also, they're highly selective of the tree hollows that they prefer. They do a multivariable analysis of their nests before they move into them. So they take into account things like the volume, where the entrance is, the entrance size, and they basically do a balanced Pareto analysis of it. And there's a lot of work that's been done on actually showing that this happens. None of the least of their abilities is actually measure the volume of a nest in the dark, right? Which is quite something in itself. I'd ask a human to do that with absolutely nothing might present a challenge. So because of they've evolved behaviors to select their nests, and then they modify them. The putting up of combs inside increases the hydraulic drag, which reduces convection currents. It's quite involved, and the honeybees are continuing to evolve.
Yes. Definite implications for Ryanair or someone, I think. I think Sukumar has come up with a similar question here. What can we learn from bees to design better buildings for humans? Or is it just a case of us learning to operate within our buildings better?
We've managed to recently catch up with the honeybees a little bit, in the sense that honeybees have been using a passive house design for millennia. The things like whether we utilize our houses. At present, we normally have our living space, for instance, on the ground floor, and then move up and then go to sleep in the upper stories. Well, that's really, in terms of heat conservation, the wrong way round. We should be keeping the upper stories warm and the lower stories cool, because they're actually working with the door open all the time. We've caught up with the idea that we need to reduce through ventilation by making our houses leak proof. Honeybees do that themselves. They actually, when they select a nest, they ignore small leaks, and then they go and plug them up with tree resin. So there are a lot of things which we have caught up, but we still, when we know, but we haven't quite implemented. As I say, so our habits of living in the Western world on the ground, mostly on the ground floor, are not energy efficient at all. But there's not only a difference of scale that we have to take into account, there's a difference of what we find comfortable. They find 75% relative humidity comfortable. They find it not a problem living in 5% carbon dioxide levels as well, whereas that would cause us some rather extreme problems doing that. So there are some things we already know about, but we don't implement them yet.
Brilliant, thank you. Okay, so I think it is time to move on. Our next talk is on towards a universal access to urban building energy modelling. Case of low-income self-constructed houses in informal settlements in Lima. I'll talk.
Hello, Tristan, can you hear me?
We can, yes.
Great. Shall I share my screen then?
by all means,
Yeah.
introduce yourself and share your screen.
Now, can you see the full screen now?
No, we can only see the slides.
You can only see the slides.
Now we've got full screen.
All right, there's a small delay. Okay. So thank you so much for having me. Obviously, it's not just myself in this work I'm presenting. There is Pamela Fennell from UCL, Sham Amrit, who is also presenting later on, I believe. There is Martin Wieser from Cook University in Lima, Ivan Korolija from UCL, and also Paul Roosevelt. So although I've put my name here very egoistically, just my name, there's a lot more people involved in this research. And over the next 10, 12 minutes or so, I'll go through a sort of a background of the project. I'll show you the challenges that we're facing in the study area. I'll talk through our methodology and the workflow of this work. I'll give out some results just to make sense of the model, really. And then I'll draw some conclusions. In terms of the background of the project, this project is part of an ESRC funding, and there's people from UCL involved, from Peru University in Lima in Peru, from CEP University in Ahmedabad, India, and sort of organizations on the ground that help us understand the situation, such as Senka, CEDRI, and MHG. The context, I think it's more well known by now that by 2050, the urban population will grow from 4 billion to 7 billion. And 90% of that growth will be in the south, in the global south. And the way that this has been happening until now is through unregulated and informal settlements. Lima, it's one of the biggest cities that are in the center of this problem. It's got about 10 million inhabitants, out of which at least 30% live in this informal settlements, where low-income and self-constructed houses are just getting more and more and more. It's really staggering, the situation. Overall, the aim of the project is to contribute to inclusive decision that leads to dignified housing and habitat by developing tools, and by that we mean mainly urban building energy modeling tools, like and inform better planning. And the focus of the work is to address the invisibility of these informal settlements in urban building energy models. I will show you, because we've written the paper, we've done the research, and the month after we've visited Lima, where we encountered the actual problems in these informal settlements. We visited 3 settlements that are at different stages of their development, but they all have very similar problems. And one of them is the hostile terrain. It's in many occasions it's the land is very, very steep, and you can see how people kind of built their own terrain to house their building, and that is mainly by stacking up all these rocks using concrete, but also using whatever mud comes out from the land. And when you're there, there's a constant drilling. There is a constant drilling 24/7 that happens. And that really indicates the rate at which these buildings are constructed, which is non-stop. It's really amazing, not in a good sense. So there's buildings made out of brick. The first stage of the development is wood. Usually, you can see here on the left-hand side, the blue buildings made out of wood and a metal sheet roof. The next stage, when people are better off, they construct brick-based buildings. And then if they stay a little bit longer, maybe you can see here on the left-hand side, there is a concrete, a building out of concrete. So there are different stages of development within that hostile terrain. And all these buildings are self-constructed. You can see here there's these two guys. I think they were either taking the roof off or putting the new roof in. I wasn't quite sure what was going on. But in the majority of the settlements, the roofs are metal sheets. And that, of course, has very big implications on thermal comfort, both in summer and in winter. The build quality you've seen is just not great. Even in this building, which is the latest construction that they have, the newest, it's a drywall house. It's the one on the left-hand side, left bottom in that photo. Still, the roof is so thin, is that corrugated sort of concrete material, and it just has holes everywhere. And infiltration in these houses is as high as it gets, probably. Another problem in modeling these buildings is that very often they have businesses within their houses. So it's not just a case of simulating, 9 to 5 occupancy of some sort, and it's really significantly more complicated. In a more centralized, really old, one of the oldest settlements. One of the things that we came across, and it's something that you can see from the images that we have from drones, is we just don't know what happens between closed doors, and there are many of them in many cases, but we just don't know what's behind them, and we've used drone flights to understand more of that, but still there's a lot of things that could be happening behind these closed doors. It could be a whole lot of communities, 50, 100 households. It could be really degrading conditions, or it could be even car parks or all sorts. And in a way, this has not informed our methodology as such, but it really has made us aware how we should be going about it, and what are the challenges that we should be looking at, other than the tools themselves. Introducing the workflow. There's 2 steps in here. One of them is how we deal with the images and how we build the volumes in the model. And it's the model itself, the simulation, calibration, the results, analysis, and visualization, and all that. We've managed to do it within QGIS. The model that we're using is based on Energy Plus. Ivan Corlia's work. He has developed what we call SimStock, which is really a Python-based script that can batch simulate loads and loads of buildings together. And then this SimStock tool, we are able to operate through a platform that Sham has built. I think he's presenting after me or maybe the one after. And he's built that very, very interesting platform within QGIS where we can run SimStock and essentially loads of energy plus simulations through this open access software. I'm not going to go into the details of that because I think Sham has got loads and loads to say. I'm going to go into how we process the images that we take. We've had about 10, 11 drone flights in the area on the left-hand side. The ones with the red pins is the area that we're looking at. And in the middle picture, this is within the red boundaries. And I have simulated these 3 building blocks that you see on the right-hand side. Now you'll ask me, how can you see 3 building blocks in here? And I'll tell you that this is so dense that you really, really have to zoom in to understand where the blocks cut off and become single building blocks. One of the things that are the biggest advantage with using drone flights is that we can see a lot of greater detail what happens in these neighborhoods, and its photogrammetry that we used is so much clearer than the satellite images. Although there's money and effort going into this process, it really has so many advantages. And one of them is realizing the volumes of the buildings, but also the materials that these use. I've got a small video here. I'm not going to let it run for too long. This is the drone flight images and the context capture software by Bentley, which takes everything, all the images, and it stitches them together and it creates this 3D mesh model where you can zoom in very, very closely. Of course, I haven't zoomed in this video because there's ethical considerations here, because we can really look at the backyards of everybody's house. But you can see, I hope, with some clarity that we can inform our building models a lot more than just having a 2D satellite image. I'll stop it here. So we create the model in QGIS. We take these photographs and we create the polygons, and then we put them through this SimStock software, which operates through QGIS. I'm not going to go into great detail, and that gets all these buildings get simulated. There's about 170 buildings or so in here that get individually simulated, and then we get the results. And we can get them both in temporal order, which is what we have here. I'm not going to drill into the results too much because it's more of the workflow that we're interested. The results right now really make sense of the model, which says, okay, the higher the floor in these buildings, the higher the temperature, and the lower the floor in these buildings, the lower the temperature. Which is in many cases what we could be expecting. Through the QGIS platform, there is a big advantage where we can see and visualize the results spatially. So this is an annual maximum temperature per thermal zone, which is each floor is a thermal zone at the moment in the model. So you can probably see, of course, by going to floors 4, 5, 6, and 7, there's not a lot of buildings that have floors above 4. So, we can have a significant result, but hopefully, from floor 1 to at least floor 4, we can see that the temperature, the internal temperature gets higher. So, and we can see where that is in a spatial resolution. And that really is the advantage of QGIS. There's a lot more things that we want to do with it. and they are developing as we speak. A few advantages, limitations, and future work in this line of work. So in terms of the inputs, there's a cost associated with capturing the images and flying the drones. The context capture software does have a license, although it's free for academics, but it does come up with a license. We would like to come up with an alternative here. Future work is extracting the footprint of these buildings and have an automated workflow for that. Of course, our model is free and it's open source, and the simulation engine is as well. It's a SimStock and Energy Plus, which is freely available. We will be calibrating the model using internal temperatures and surveys, which we have already done. We've measured internal temperatures in many of these homes. We also have, surveys, interview surveys with many of the house owners. Of course, our calculations engine is state of art, and our analysis is preliminary, but it's quite promising in its visualization advantage. A few conclusions. I'm a bit out of time, but I'm closing now. We've seen it's a freely available open access platform, which is what we want to have out of this project. We want to have something that anybody can use. Our workflow is transparent. It does have limitations, and the work that we will be doing in the next year or so is look at retrofit at scale, especially retrofitting these metal sheet roofs in many of these settlements, using the internal temperatures that we measured, and with our modeling and calibration, we can map the health risks across these settlements, at least in terms of high temperatures and low temperatures as well in winter. There's a lot of land trafficking and eviction of residents happening, so we want to map this throughout the settlements. And one of the work that we have initiated is looking at the representation, the actual representation of people in our model, because these simulations, we run them with a standard 9-to-5 schedule. That was all for me. I'm a minute and a half over. My apologies, but thank you very much. Any questions I can either take now or later in the end. Thank you.
So we have a good question here from Rob McLeod about what sort of validation have you done to confirm the accuracy of your model?
So this is a preliminary model. Thank you, Rob, for the very interesting question. I'm not only working now on the calibration of this model. We will be calibrating the model using mainly internal temperatures. So we will be doing a two-step calibration, if you like. We will be calibrating a few of these box-shaped buildings that you've seen, using internal temperatures and using parametric analysis. But we will also, and then we'll take this forward. We will propose some sort of retrofit for the specific buildings, and there's a lot of work for that going forward. But then, apart from the parametric analysis in these few buildings that we will do, we will also implement a Bayesian validation approach on the large scale of the models that we will be looking at. I've only shown 170 buildings or so here, and they're all kind of shaped as boxes with some sort of openings. But we have data of drone flights and this sort of context captured 3D models of thousands of buildings in this 3 settlements we're looking at Lima. So I've initiated the parametric analysis in the few buildings, but now this next step coming in January is the Bayesian calibration of the large scale. Now, in terms of accuracy, this work was not really concerned on the accuracy as such. So I'm not sure. So I didn't really go in detail in the results, but there has been, so the model gave out internal temperatures of 50, 55 degrees, which is not really logical 100%. But we were looking at the methodology and the workflow, so set up this open access, freely available, if you like, transparent methodology, and then improve that as we go forward. We have measured temperatures of 35, 40, 45 degrees in some of these homes. So at 55 might not be, you know, out of the real world, but and we have done some sort of this parametric analysis that we're doing, and it comes really close, with the maximum internal temperature between model and measured being just a couple of degrees off, but it's still not great. So the other thing with this validation calibration is that there's not a lot of things that you can change in this model. You know, you can play with infiltration, you can play with some of the variables in the materials, but they're not complicated buildings. So I'm not expecting it to be super complicated as such. Sorry, I've spoken for way too long.
Okay. So we have one last question here from I can't pronounce his name, sorry. But yeah, in the chat there, which again is about the validation. So why have you chosen internal temperatures as the calibration process?
Because this is all we have.
Is all you have.
Because these people, in many occasions, they don't have heating or cooling in these houses. Let me clear this up. So that's why in the winter it gets quite low, and we were there as their winter was ending. It was like September, or like end of our September. This is end of our summer, but really is end of the winter, and it was really cold up there. It was very humid as well. So there's no energy being used as such. They have this gas canisters that they could be using to cook, or they could be using solid fuel to warm themselves. So there's no real data other than internal temperatures and humidity in the majority of these homes.
So given the large uncertainties with construction, the use, have you considered using this model for the global north just to try and validate it and make sure it's giving you an appropriate answer?
That's a really good point, Tristan. I think so. We had the SimStock, the engine has been used, in Camden City Council in London, or Islington Council in London. So there has been work that SimStock is a validated, if you like, and accepted engine that, whatever it does is just it takes a Python script and it just does many energy plus simulations.
Yeah,
now,
but as with every other simulation, if you feed it rubbish, you'll
exactly. The one that we have developed, and Sham has been really the main developer behind the QGIS engine, it has been developed mainly within the merits of this project, which is looking at the global south, and it's looking at how we can make these tools available. That's why we selected QGIS as the main engine and main interface, if you like. But it would be, I think your point is really interesting, and it might be a really interesting exercise to present, two different blocks. One, as you say, in the global north, one in the global south, same workflow, and see what one with a lot of probably variables, but a lot of data to validate, what one with fewer variables and fewer data to validate, and see how this compares. That would be very interesting. Thanks for the idea.
No problem. Okay, we're a little behind, but I'm sure we'll pick up the time. Our next talk is from David Jenkins, talking about tailoring demand reduction strategies for communities in India. Over to you, David.
Good afternoon, everyone. Hopefully you can see my slides okay. I'm Dave Jenkins from Heriot-Watt University, and I led the CEDRI project, which I'm going to talk about a little bit in tomorrow's showcase event as well. But just to give you an overview, this was a 4-year Newton Baba funded project through EPSRC, collaborative project between UK and Indian partners. And we were trying to look at designing energy demand reduction strategies in Indian communities that reflect three sort of pillars of the project. One's around the evolution of the built environment. One's around local network constraints, so trying to understand the energy systems that are serving those buildings. Also, we wanted to try to understand the behaviour of the household, of the actual households themselves, for the communities that we were studying, particularly in relation to energy and cooling. So those are the three kind of components of the project, the different strands of the work. On the network modelling side, we were looking at how to define different local network characteristics. So voltage, frequency, the sort of standard parameters that we use to understand how that network is performing. But also trying to understand the evolution of those grids as the built environment changes, as the needs of that built environment changes, then the local grid and local energy systems have to respond in due course. And therefore thinking of the network resilience to future change as a result mostly as a result to changes on the demand side that we might imagine will be happening. On the demand side modelling, which is perhaps a little bit more relevant to this conference, we had two different components of that work. One was around demand synthesis, which I'll talk about in a little while. So trying to take real demand data, real electricity demand data of buildings in India and trying to synthesize equivalent profiles. And I'll talk about why we might want to do that. And then the other component is more, if you like, traditional building simulation using dynamic simulation packages to try to understand the impact of various measures on the internal environment of some of the buildings we were looking at. But we were majoring quite a lot on understanding of the people using these buildings and trying to understand what that means from a building modelling perspective. How do we accommodate this information that we're gaining about how people are using their buildings? So we had a series of surveys and workshops, some co-production exercises, where we're trying to pinpoint the reasons for different behaviours that we might observe in the energy data, so we can directly engage with the people that are actually producing these demand signals. Also trying to understand if we did come along with energy demand reduction strategies, how would they be accommodated by the households that we were talking about? This idea that as building modelers, we shouldn't be trying to inflict demand reduction strategies on communities without properly understanding those communities in the first place. So as a model, if you're approaching a project of this scale where you're trying to understand both buildings, but also the surrounding energy system serving those buildings, you are going to engage with lots of different types of models, different tools, different assessment protocols. And the first question that we might ask ourselves is whether there needs to be properly hardwired integration between those different modeling components. Are we looking to construct a kind of mothership energy model that can do all things for all people, or are we trying to take a different kind of approach? So on the left-hand side of the slides, this is the kind of data that we were collecting, or the kind of data that anybody doing this exercise might try and collect. So the physical information of the buildings that we were looking at, workshop, interview, data describing things that people are actually doing in those houses and how they approach energy and how they approach cooling in particular, climate data and weather data, metered demand data from a sample of the homes that we were studying, and local network information as well in terms of how the grid is aligned and how that's set up. So you might collect all this kind of data. When you start to think about all the different sort of modeling components that you might run this data through, there's quite a different, these might be individual tools, or there might be certain components of certain tools. You are potentially going through several different processes when you try to model different modeling applications of this data. So our approach was really more a sort of toolkit approach, where we either used existing tools or developed our own tools to perform certain exercises. And then it's just a case of creating the right sort of chain of information through those different components to answer specific questions. So if you're asking a question which is more about demand reduction of individual buildings, then you dip into a certain selection of these different modeling components, but you don't necessarily need to get involved in every single tool in the toolkit, if you like. Whereas if you're looking at demand reduction on the network scale, when you're thinking about aggregating the buildings to a level that actually means something on a network scale, you might be doing slightly different forms of modeling. But the key point here is that they're not entirely distinct. They're using common data sets, they're using common assumptions, but it's a slightly different modeling journey depending on the question that you're trying to answer. So that's the kind of philosophy we took for this particular exercise. Just trying to identify that when you have a project involving energy systems, wider energy systems and energy networks and buildings themselves, you are going to potentially kind of encounter numerous modeling software and tools. The case study that we're particularly concerned with for CEDRI, or the one that we probably studied the most, is a sustainable community in Tamil Nadu called Auroville. So this picture you can see on the right at the top is a kind of model, a physical model of the community itself. It's got a big gold temple in the middle, which we didn't attempt to model, I have to admit, but we were more focused on the residential buildings in that community. So I'll speak a little bit tomorrow as well about the reasons for selecting this community and the idea that it's not necessarily a typical Indian community. But for the modeling tasks that we wanted to sort of test and try out on this community, we were looking to synthesize demand profiles from monitored data, as I've already suggested. We were looking at physical modeling using dynamic simulation packages, so we could test out different demand reduction solutions with a particular focus on alleviating high cooling loads, or potentially mitigating for future cooling loads. Understanding the local drivers of energy behavior through engagement with those communities, and trying to understand what that means in the context of change, the change that those communities are likely to experience over the coming years and decades. And then trying to take all that information and construct sort of future energy scenarios, future energy demand scenarios that account for things that are likely to happen with buildings, with networks, but also, as I keep saying, the communities and the individuals themselves. On the demand synthesis component, so we have the kind of data that we were collecting is in the top right of this slide. So that's measured electricity demand data for a day for one of the buildings that we were monitoring. Quite uneventful for a demand profile, I guess, compared to some other countries, but you have these kind of cooling spikes and other spikes in the demand profile, but the baseline demand profile is quite low. There's a relatively low penetration of consumer electronics and so on in some of these buildings. So what we were trying to do is to take that data and run a seasonal trend decomposition process, STL decomposition process, to split the demand profile into constituent signals, so we can identify fairly stochastic profiles, but also profiles with different periodicities, pull those out as individual component signals, potentially then model those individual component signals separately and have a look at how they might correlate with external weather variables or information we might have about occupancy and other things like that. And the benefit of doing that is that we can then take a sample of, say, 30 homes or whatever it might be, and try to upscale that to a series of synthetic demands that correlate with, say, 200 homes or something of that scale, providing we weight the sample appropriately and so on. And what that allows us to do is take that jump from individual building demand profiles to something that's more meaningful to a network scale or a substation feeder level. So we use this as part of our aggregation process, but it also allows us potentially to morph for future scenarios, because we can look at, for example, how weather data corresponds with the demand profile values that we were seeing. So we created a climate module to future morph some of these profiles. But we can also use them for our network models, where we can take the nodes in that network model, where the nodes are basically individual properties, and we can populate those nodes with data that's generated from this synthesis approach. Just to give you an idea of what the aggregation looks like. So this is for a couple of months data. In dark is the baseline data for something like 200 properties, electricity demand. So you can see that cycling on and off, and then we can morph that for a future weather file based on a correlation that we've investigated between the weather data we have for the baseline case study and the demand data itself. So this is all published and described in more detail elsewhere. Just a note on that network modeling. Again, we can populate those nodes with baseline data to see how the network responds to those demand levels. We'll also do the same thing with this future scenario. We're slightly restricted for that future scenario because we need to be able to quantify we can only include effects that we can quantify. So we tended to focus a bit more on future weather and also occupancy profiles and existence of cooling systems and so on. And so we can start to think about whether the network can cope. And just quickly as well, on the dynamic simulation that we ran some Energy Plus models of some of the buildings that we were studying in the Auroville community, trying to look at times of high cooling demand if cooling was present, and if cooling wasn't present, to look at times of heat stress and very high temperatures, which we observed. Again, this is published elsewhere. But it was interesting to link up the demand profile shapes that we were seeing with the kind of modeling shapes that we were generating, but also the behavior that was reported from the households, to try and get some kind of commonality between those three different forms of data collection. I'll talk about this a little bit more tomorrow for those that are able to come to the showcase on the Newton-Baba projects. But the social science part of the work, we ran interviews and questionnaires, trying to understand cooling preferences, trying to understand what a typical household was in this community, their approach to energy saving behavior, their openness to future measures such as time of use tariffs and so on, anything that might be done to change the demand characteristics of those buildings, developing sort of co-designed local policies that might work with dealing with high cooling demands in the future. And we also ran a co-production workshop with practitioners as well from the energy industry, trying to get to the bottom of the concerns that they have around how local energy networks might need to evolve to cope with rapidly changing demand characteristics of the built environment. Again, this is all published. So very quickly to finish off, in terms of the findings that we came up with, so there's a clear need to match demand reduction strategies to specific communities with an understanding of future change. So that's kind of self-evident, but that really does come home when you take models that perhaps have been designed with, say, UK building stock in mind, and you try to translate those models or port across those models to a very different locale, very different building stock, very different activities and technologies, and you understand that actually the kind of data that you need to gather as a building modeler is somewhat different as you move that to a different geography. And overgeneralization of occupants in particular, we like to gloss over occupants sometimes as building modelers. This is they're a key component of the buildings that we were looking at. And demand synthesis can help with linking building demand scenarios with network models. So those working in this field where you're trying to understand buildings and networks at the same time, there is this jump of scale, which we always try to cross over as modelers. We think the demand synthesis approach we took is a really useful way of jumping up scale. So you can say something about the buildings, but you can also say something to those working at network level. But all these strategies require modes of communication with the householders themselves. And we've proposed methods of doing that. Obviously, it's not always possible. But we've kind of we think there's clear importance in communicating with householders in the way that we've described. Physical building simulation obviously plays a role, but we do need to kind of define why we're using this and how it sits in with other methods, rather than just sort of modeling buildings because we can. Obviously, with highly efficient building simulation software now, you can basically model what you want whenever you want. But that requires you to maybe rethink why you're using building simulation in the first place. And in India specifically, the challenge is obviously trying to manage an inevitable rise in cooling-driven electricity demand. There's a fairly low penetration of residential air conditioning in India right now, which was spoken about in one of the keynotes this morning. So we're projecting very high, very rapid increases in cooling-driven electricity demand. So how do we manage that? Probably not going to reduce it, but how do we manage it and look at sort of demand shifting and demand management programs to create a more acceptable scenario for people operating on the grid level. I shall finish there. Happy to take any questions. Thank you.
Thank you, David. Before the questions rush in, I'd like to quickly jump in there, if I may. Your last point about people moving from rural areas to urban areas, and they're not using air conditioning in the rural areas. Are they using the buildings correctly in the urban areas once they have air conditioning? Or are they still trying to operate them in a more natural ventilated way? And how can you manage that sort of changing?
Yeah, so here you have to be really careful, or I have to be really careful to overgeneralize the communities that we were actually looking at. So we were looking at an intentional community, a sustainable community that had a certain approach towards cooling. And their approach was basically, we don't want any cooling. And what's interesting there is how that kind of mini culture, if you like, has evolved over time, because as a result of climate change and experiencing even warmer temperatures, but also having advice from their GPs about the danger of having very high temperatures in their properties, they've started purchasing cooling systems, whereas 10 years ago they just wouldn't have done that because culturally they were against cooling systems. But what that does mean is that you have, at some level, a fairly sort of, I wouldn't call it exemplary, but a very sort of miserly approach to cooling, because it's seen as a fundamentally bad thing. Now, if you take another community of, say, an area with a sort of growing middle class, and the middle class in India is projected to grow substantially in the next 10 years, 20 years. If you begin to have cooling as a kind of aspirational technology, or just a default technology that's expected in homes in the way that it hasn't been in the last sort of 10 years, you can't really guarantee this same kind of miserly approach. And this is the kind of key point of CEDRI. You cannot generalize the findings of one community to a completely different community. You have to, the process, the methodology, we believe, is replicable, but the results of that are not necessarily generalizable, which is why you need this engagement with communities, because you'll find very different, depending on socio-demographics, depending on the sort of economic situation of those communities and geography as well. You'll have very different responses to even just cooling on its own, never mind other forms of energy consumption. So yeah, I wouldn't want to generalize that. In the communities that we looked at, it was this miserly approach to cooling that was present. But we were dipping into that community at a point that this was changing from what it used to be.
Very interesting. Are there questions from the floor? Nobody's typed anything in. Looks like you've got away with it, David.
That's good.
I'm sure we'll look forward to your to the talk tomorrow on the CEDRI project. I will learn more.
Yeah. Cheers. Thank you.
Thank you very much. So our next talk is from Shyam, developing an open access plugin for urban building energy modeling in QGIS. Over to you, Shyam. I think you're muted at the moment.
Thanks for the introduction. Yeah, I have sent in my recording that will be played now, and I'm glad I did because I have a sore throat today. So I'll be here for the Q&A afterwards. Thanks. Hello, and thanks for the opportunity to speak today. This talk will be around open access urban building energy models, and specifically we'd like to present the initial development of a free and open source tool that can be used to set up and perform dynamic thermal simulations over a large number of buildings. I'll first talk about the need for open access tools in this field. I'll talk about UCL's SimStock modeling platform. Then I'd like to introduce the early development of a QGIS plugin which can set up and perform urban building energy modeling. And finally, I'll end with some use cases where the plugin has been used and what can be achieved with it. There's been a substantial increase in interest towards urban building energy models in recent years. However, the literature suggests this is mainly concentrated in the US, Europe and China, and coverage is notably absent in South America, Africa, Southern and Southeast Asia. So to enable more widespread use of urban building energy models, particularly in the global South, we must address a number of barriers. So affordability is a key one because the licensing costs for tools can be prohibitive for some people. Tools only accessible via a single operating system restrict access to those with access to those operating systems. Specific input data formats can create a significant amount of work, which leads to the other point where the requirement for specialist knowledge, especially around programming and coding, can restrict the access to those with a background in this area. So some tools have addressed these issues separately, but none of them have successfully attended to all of them. I'd now like to talk about the SimStock modeling platform, which was developed by a team at UCL. It can automatically generate stock-level Energy Plus models given a set of input data. It automatically pre-processes the geometry data to prepare it for Energy Plus, and then combines this with user-specified data on, for example, heating systems, the internal gains, and schedules, and so on. It can also address complex cases, such as mixed-use buildings, and SimStock has been used in a number of published works. However, this has often been in close contact with the research team who developed SimStock because it requires knowledge of Python to be used, and therefore is not as accessible as we would like. So this leads us on to the next slide. We'd like to introduce the SimStock QGIS plugin. This provides a simple and accessible interface for urban building energy modeling and is cross-platform. Both QGIS and the plugin are free and open source with a complete graphical user interface, so there's no knowledge of coding needed to use either of them. With the plugin, there's also no need to directly interface with Energy Plus, but the model objects are still editable, meaning it is not restricted to any predefined cases and can accommodate varying levels of complexity in the model. And finally, since it outputs the results directly back into QGIS, this platform has extensive functionality for analyzing and visualizing data in this format, which we think will be very powerful in the future. I'd now like to give a demonstration of the plugin in use to show how an Energy Plus model can be developed and simulated, starting from a simple set of blank polygons. So here we have a series of blank polygons opened in QGIS, and you can see in the attribute table on the right-hand side that these all have no attributes associated with them. If I just open the full table, it's all blank here. So these polygons can be sourced from anywhere. In this case, they were sourced from the UK's Ordnance Survey master map, but these can be hand-drawn, or any source of polygons will be fine for the use of the SimStock plugin. So the next thing we need to do is add in the expected attributes, which SimStock will use to create the Energy Plus models. So if we launch the QGIS plugin, we get this interface. Now the initial setup is something that will be run on the first time, but we can select the layer that we're interested in and select Add Fields. And this will add a new layer, which can then be populated by the user. So here we have a number of fields that has been created by the plugin. Each of these needs to be filled out by the user. So I haven't got time to go into what every field means at the moment, but this layer will be editable, and this can be set so the height, for example, of the building can be changed, and all of these fields can be filled out by the user. And these are the basic inputs that SimStock expects. And to save time, there's one that's already filled out, which I can go to now as an example. So this is a fully filled out attribute table as SimStock would expect for the given polygons that we saw on the screen. A number of these buildings are just shading blocks, the ones that say true, so they have fewer pieces of information in the attribute table than the ones that are not shading blocks. And as I said, I can't go into every field in detail with the time that we have, but these mainly are per polygon inputs, so the height, the window to wall ratio, the number of floors, and so on. You'll see that there are construction and use fields as well, and these refer to the database. So this is another way we can specify input data for the model. So this is the per polygon way, and we then have the database, which I'll show you now. So to load the database, we launch the SimStock plugin again. We can set our current working directory, and when we set the working directory, we get a number of database layers. So you can see them all on the left there. And these are layers in QGIS which contain no geometrical aspects, so they're just layers with no geometry, but we can view and edit these as well. So if I take the material layer, for example, and open this, each row pertains to a different material in our model. And if I view it in a slightly more, in a slightly better way, here, each entry here is a separate material, and each field here can be viewed and edited by the user. So I can turn on edit mode here and change any of the materials, for example, and the material fields that I'd like. And these will all be taken by SimStock and used to create the Energy Plus model in the end. And you notice some of the fields in the attribute tables of the polygons refer to constructions. So they will refer to any constructions that are contained in the construction database layer. And this is how most of the database layers work. So the database essentially provides a way of customizing the Energy Plus models before these models are created. So finally, we need to run SimStock and the Energy Plus simulations. So finally, we go to the plugin, we select the layer of interest. So the one I filled out is testing_1, and I click run, and I can use multiple CPU cores to do the simulation. So this will take some time. Simulation is complete. So we can look at the created layer. We see this new layer here. I'll just move it to the top. And this is our results layer. So if I click on one of the attributes here, we see we've got a number of new fields added. And these are our results fields, the results from the simulation by floor. So floor by floor, they are reported. And these are just some example results given the case that we were looking at specifically. But the idea is that any Energy Plus outputs can be selected for these outputs. So here we just have some temperature thresholds, electricity consumption and associated CO2 emissions reported for each floor. And if you look at a shading block, for example, this one, there will be no results because this was not thermally simulated and only used for shading. All of the Energy Plus files and IDFs and outputs can also be viewed, and this will be output in the user's set current working directory. So this is the working directory I set, and there's a folder here called IDF files. If we open this up, we see all of the IDFs, and in each of the folders we'll have the Energy Plus results. So these can be looked at by the user if necessary and interacted with for a more detailed outlook on what was going on. So this summarizes the use of the SimStock plugin. As I've already mentioned, it's in an early stage of development, so some of the details and the workflow may change slightly, but the overall process from blank polygon to Energy Plus model to final simulation results is the key part of the SimStock QGIS plugin. We'll now look at some work which made use of the QGIS SimStock plugin, and this work focused on 3 blocks of buildings in the informal district of El Agustino in Lima, Peru, and the chosen block is shown here in this figure. The polygons shown on the right were hand-drawn with the help of data from a drone survey, and this resulted in 165 buildings in total. The heights were calculated from a digital elevation model produced in QGIS, also with the use of the drone imagery. The fabric and the internal gains were estimated based on local knowledge from experts in the Pontifical Catholic University of Peru, as well as the drone images for the fabric too. HVAC systems are rarely present in this region, so these were excluded from the modeling, and a local weather file was provided to the plugin to perform the thermal simulations. After specifying all this input data in both the attribute table and the database, the SimStock QGIS plugin then created the Energy Plus models, simulated them and pushed these results back to QGIS, and this is what we're seeing on screen here. So these results focused on maximum indoor temperatures by thermal zone from floor 1 to floor 7, and these were visualized in QGIS. And normally visualizing the results in this way from a bunch of Energy Plus simulations would be a long and manual process, but in this case with the SimStock QGIS plugin, this is only a few commands in the QGIS session. As I've already mentioned, the plugin is in early development, but we do have some future development goals, such as retrieving any Energy Plus outputs from the model, some improvements to the database, for example a database manager, and making this more collaborative, perhaps hosting it online, the ability to split each floor into separate thermal zones with different uses, and the inclusion of definitions of different HVAC systems to automate this process, and finally the support for uneven topography and moving on from a flat earth model. Thanks for listening, and please let us know if you have any questions, and 2 of our emails are provided here should you wish to contact us.
Excellent. Nice presentation, Shane. Are there any questions from the floor? Here's one from Isha. What is the model algorithm used for solving the model? Is it coupled with Energy Plus, or does it simulate models within QGIS itself? It's a nice easy one for you.
Sure. Yeah, so the actual model simulation is done in Energy Plus. The plugin includes a version of Energy Plus packaged within it, so it can automatically, SimStock essentially creates the Energy Plus models, the IDFs which you saw at the end, which are these Energy Plus model files, and the plugin can internally simulate these, push and retrieve the results that Energy Plus has produced, and retrieve these back into QGIS. So QGIS is mainly the interface with which you can interact with the models and view the results, but this QGIS itself doesn't do any of the simulation. This is all done by Energy Plus.
How do you get the profiles for Energy Plus into the model?
So do you mean the stuff in the database, like the schedules and so on, stuff like that?
Yeah, so the building use, how do you replicate the diversity of real people?
Right. So this is always a challenge with any model you create. The idea with the plugin itself is that there's as much flexibility in how you do this as there would be interacting with Energy Plus directly. So if you were to be creating these Energy Plus models directly via some other traditional method, or for example using Design Builder, which I think some people use, you'd have to decide how detailed you want to go with the schedules, whether it even makes sense to go that detailed if you're making a lot of assumptions there, because occupancy, as we know, requires a lot of assumptions a lot of the time, because we don't have the data to model that. So the idea with the plugin is you can go into as much or as little data as you, as much or as little detail as you need to do, and that you would do traditionally anyway. This just gives a kind of way that people who don't have experience with Energy Plus or with coding can create these model objects in a much more simplified way. So to create an object in the database, we hope, is a much more simpler way than doing it directly with Energy Plus. I've done both, and I do find the QGIS method to just be much more intuitive in how you construct those things. So yeah, you're right to raise it. It is a big challenge, but it's not something that the plugin claims you can just forget about. You do still have to make these considerations.
And are you making it for all the buildings, or could you have each building different from the others?
You can, yes. Yeah. So it supports different uses. So you can assign a blanket schedule to them all if that's what you want, but you can also within the attribute table specify, for example, a use for the building. So this could be just dividing it by commercial and residential, something as simple as that. But you can also have multiple residential presets, which you then input your own residential schedules for 1, 2, and 3, and then assign those to which houses you wish to apply those for. So there is flexibility in that respect.
Interesting looking tool. Okay, we've got a few questions from the floor now. We've got one from Nick. So how does the workflow look when generating urban geometry in cities with limited municipal urban data? So OpenStreetMaps is not available everywhere, and you can't always fly a drone.
Sure. Of course, yeah. So I guess with those two bits, you're touching on the geometrical aspect. So as I've said, we can use hand-drawn polygons as the input. This will be likely much more difficult without the access to OpenStreetMap data, as you've said, or drone surveys, but it's still a possible input. Wherever you've sourced these polygons from is a valid geometrical input. Obviously, in the case that you hand draw them without those, there might be more questions about the accuracy of them, but that would be something that you'd have to just bear in mind when you analyze the results of your model and so on. With the non-geometrical aspects, I've kind of already touched on that, but in some of these places, in fact, even here in the UK, we don't have the data we'd like for occupancy and stuff like that. So yeah, with the non-geometrical aspects too, if you didn't have access to good data, you'd have to state your assumptions clearly. But with the plugin, the idea is that you can view everything is viewable. Nothing is a hidden assumption there. The database shows you all the assumptions you've made. or that the presets are making, and then you can state that clearly in your results. Hope that makes sense.
Okay, we've got a question from Sam about how you handle glazing.
Sure.
Using the building height.
Okay, so firstly, with the glazing, we use a window to wall ratio in SimStock. So this is just a percentage, an estimate of the window to wall ratio, and this will place a single window on each facade to emulate that opening. And we've found with some studies in the past where the actual specific placement of the windows, I think, is not doesn't make a great difference to the simulation results. So we found that the window to wall ratio handles this in the best way. And the inaccuracies in building heights acquired. Okay, so we don't necessarily source the heights from QGIS. This is something that has to be input by the user for each polygon too. So this isn't the inaccuracy there isn't something we directly deal with. That's kind of one of the inputs we ask the user to provide, and also the number of floors, so how that building height is split up into separate thermal zones. So yeah, we don't really deal with the inaccuracies there directly.
So building on that, you say you use a window to wall ratio.
Sure.
How many zones do you put in the building? Is it just one zone per floor, or are you creating rooms within these buildings?
Currently, it's one zone per floor. So when you specify a number of floors, it will be one zone per floor. We're looking into how to have, as I mentioned right at the end, how to split each floor into, say, multiple uses, or whether there are different circulation spaces and things like this, which need to be modeled differently. But that's not currently, it will be something we'll try and implement.
Okay. We've got, if you're making the model from QGIS, is the LOD an issue?
I must admit, I'm not very familiar with GIS. I have used QGIS, but the actual GIS as a field, I'm not so familiar with. So I'm not sure how to answer that question. The only thing I'll say is the level of detail that we require for these models, as I've said, it comes all from the database. So anything the Energy Plus model would require to simulate something like this is stated in the documentation, and these are the inputs that we require. It's kind of a fixed set of inputs, so you wouldn't be able to leave any of them out if you were doing the modeling work. You would have to specify something there, but if you had to make assumptions, then that's possible. It would just be that aspect has been assumed. I hope that, I'm not sure that answers your question, but I hope it did. I think one more is there.
So we've got one from Parag here, radiative exchanges from the surroundings.
Yeah, so the Energy Plus model, Energy Plus models are dynamic thermal simulations. So they do capture the surroundings and the building positions with respect to each other, so that if they're, for example, touching or close to each other, then there will be heat flow between those. Also, as I mentioned, you can have shading blocks too, so that will be considered when doing, for example, the ray tracing path from the sun. The shadings will be taken into account there. The ground, sorry, yeah.
The radiative exchange from all the buildings you're simulating will be considered, but what about the surrounding urban area and topography?
Sure. So the surrounding area in terms of the infrastructure will need to be included as shading as well, and that is how. If that's not included as shading, it won't be considered. So any surrounding infrastructure will need to be specified as shading, which can be done here as well. The topology of the area is something we want to include in the future. So I mentioned at the end, we're currently using a flat Earth model. So the the geometry of the ground. The ground itself is included in the thermal simulation, but the topography of it is not, and that's something we'd like to expand to in the future.
So what was the computation time, and were you simulating all the buildings in the scene, or just?
Yep. All the buildings were simulated, and this was done locally rather than on a server. And this was done on my colleague's laptop, Argyris, who just presented to you 2 presentations ago. I believe it took about 10 minutes on his very powerful laptop. Yeah. No, not just the target building. Was all buildings in the area. Yeah.
So all 170 or however many were sampled, simulated. But
it must be said that this was a fairly simplified model. This, as he's already said in his presentation, that there aren't we don't tend to see HVAC systems here, so that reduces the computational load by quite a bit. So if these were present, we would expect it to be quite a bit longer. But yeah, for this area was about 10 minutes, I think.
Yeah, very good. It's a powerful looking tool.
Thanks very much.
Okay, I think that is it for this session. We have a few minutes now until the fireworks and the debate later, so we have time for a comfort break. I'd like to thank all the speakers who've given us such interesting talks, and for those of you that have engaged by asking questions, thank you to you too. Hopefully you found it interesting, and any further details can be found in their papers, which are on the website. Thank you very much.